Howdy! Welcome to Elementary Statistics. I am Lance Curtis. This is the lecture for Section 4-2, Addition Rule and Multiplication Rule. Here in this lecture, we're going to look at two very important rules for helping us to calculate probabilities of events. We're going to start off by looking at compound events. That'll set the stage for the addition rule. And then we're going to look at Venn diagrams and disjoint events, which will set the stage for the multiplication rule. We'll then examine the dependency of events, which plays into the multiplication rule. And then we'll also wrap up the lecture by looking at tree diagrams. Key concepts in this section. So we're going to look at the addition rule and the basic multiplication rule. So when you see probabilities of A or B, that word or signals the addition rule. When you see the probability of A and B, that and is going to signal the multiplication rule. Now, keep in mind that the probability of A or B is the probability that either event A or B occurs as a single outcome of a procedure. So this word or is being used in the inclusive sense. So we could have the probability that A exists. We could have the probability that B exists. But we could also have the probability that A and B occurred together simultaneously. On the other hand, if we're looking at the probability of A and B, keep in mind that this is different from the probability of A plus B. The probability of A and B is the probability that event A occurs in a first trial and then event B occurs in a second trial. But the probability of A plus B is the probability that A and B occur together in a single trial. So it may look to be the same, and we've always looked at translating plus as to and, but seriously, you gotta understand that when you're dealing with probabilities, the probability of A and B is not the probability of A plus B. However we do our accounting when we're tallying up the tallies to calculate our probabilities, we need to make sure that when we do the math, we're not going to double count any of the possible outcomes that we're using to calculate our probabilities with. I'll get into more details with that in a moment. First, though, let's talk about compound events. A compound event is simply an event combining two or more simple events. We express a compound event with the notation P of A or B, which we read the probability of A or B occurring. This is the probability that in a single trial event, A occurs or B occurs, or they both occur. Remember, we're using that inclusive sense of the word or. How do we calculate it? Well, very simple. First, we define the total number of ways that A can occur, and then we find the total number of ways that B can occur, and then we add them together in a way that we make sure that nothing's being double counted. Let's take a look at this addition rule, which is basically what I just got done describing. Your textbook author says that there are two addition rules when calculating the probability of compound events. First, he describes what's called the formal addition rule. And this mathematically written is what you see here. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So here, we're actually denoting individual probabilities. We add them together, and then we subtract out those events that count for both A and B. In this way, we avoid the double counting scenario. Then there's the intuitive addition rule, which is just basically taking the ways that each of these events can occur and dividing them by the total outcome, making sure that we count them in such a way that we don't double count any individual outcome. I don't know why your textbook author is separating these out as to two different rules, because essentially the calculation you're performing is the same. When it comes down to crunching the numbers and doing the math, you're running the same operation. So why is it that you're actually separating these out into two rules? I have no idea. So what I'm going to teach you is we're just going to use what he calls the formal addition rule. We're just going to use that. I'm going to show you how it applies. And once you get the hang of how to do the procedure, it's very simple. Let's look at an example to illustrate. So we have chemistry professors who are preparing sulfuric acid solutions for a lab assignment. And these professors were tested to see if they prepared their solutions correctly. So here we have a table listing the results of the tests. And we have Professor A, who prepared 12 solutions correctly and incorrectly prepared 6. And then we have Professor B, who correctly prepared 3 solutions and incorrectly prepared 15. I would rather be in the class with Professor A than Professor B. Professor B doesn't look like he knows what he's doing. He's incorrectly preparing his solutions 5 times as much as he's correctly preparing them. So why he still has a job, I don't know. But this is the data that we have. So the question is, for the classes taught by Professor A, what is the probability that the students received a correctly prepared solution for their laboratory assignment? Well, we're going to calculate this just as we've seen in the previous lecture. Take the part, divide by the whole. So the part is going to be 12, and the whole will be 12 plus 6. Notice we're looking at just the row for Professor A because that's what the question tells us to do. For the classes taught by Professor A. So we're only looking at this row here. The number of correct preparations is 12, and then the whole is 12 plus 6. So we punch all this out, get 12 over 18, which is 2/3, or 66.7%. Now, for the classes taught by Professor B, what is the probability that the students received a correctly prepared solution for their lab assignment? Again, we're running through the same calculation. Take the part and divide by the whole. We're looking only again at the row for Professor B because that's what's specified here in our problem statement. So then we have 3 for the part. This is the number that was correctly prepared. 3 plus 15, that's the whole that we have. So 3 divided by 18 gives us 16.7%, which is what, 1/6? Yeah, I think that's right, 1/6. So there's a probability that you're going to get a correctly prepared solution for your lab assignment if you're in Professor B's class. Now, what is the probability that any chemistry student receives a correctly prepared solution? Well, here we're looking at the whole class taught by both professors. So now our parts and whole change. We're going to take the part for Professor A, which is 12, then the part for Professor B, which is 3, and we're going to add that together, dividing by the whole. The whole is now all 36 solutions, not just the 18, because we're looking at both classes for Professor A and Professor B. So our whole has actually changed. So we're going to add these together. And notice we don't have to do any adjustment for double counting because they're 2 separate classes. There's no overlap between correct preps for one class over another. So there's no double counting going on here. So we can just add these 2 together. And out comes 15 over 36, which when we divide out is 0.417, or 41.7%. This then is the probability that any chemistry student from these 2 professors will receive a correctly prepared solution. Again, we're looking at these 2 values here. These are our parts, and we divide it by the whole, and that gives us our final answer. Let's look at another example, which does involve double counting. So here we have a consumer survey listing response rates by age. So here in the table, we have those who responded to the survey when they were contacted and those who refused to respond to the survey when they were contacted. So we've got different age groups here, 18 to 25, 26 to 35, so on and so forth. So what is the probability, given this data, that a randomly selected subject is between 46 and 55 years old and responded to the survey. So we've got two events here. We've got one event where the subject is between 46 and 55 years old, and a second event where the subject responded to the survey. Let's look at each of these individually. First, let's calculate our sample space. This is 972. The 972 comes by adding in all of the numbers together from our survey. So we've got all possible outcomes added up together. That gives us our sample space of 972. This is then the whole part that we use for our probability calculations. The part over the whole is then going to be 123 over 972. Where does the 123 come from? Well, notice the 123 is coming from this part of the table right here. These are the subjects who are 46 to 55 and they responded to the survey. So this is our part divided by the whole gives us the probability 12.7%. Now, what is the probability that a randomly selected subject is less than 26 or more than 55? Remember that word or is going to signal to you that you need to use the addition rule. So let's use it. Here we have the math all laid out. So the probability that we have less than 26 or more than 55 is the probability of the first, less than 26, plus the probability of the second, greater than 55. And then we're going to subtract out those events that double count for both so that we avoid the double counting. So here we have 65 plus 12. This is the probability of those who are less than 26. 65 and 12, notice, comes from this portion of the table right here. That's the part for the less than 26 event. Now we're going to get the greater than 55 event, and that part is listed here. So we want everyone that's over 55. We're going to add all those numbers together. That's going to be the part for this event B. And then we're going to divide it by the whole. And then notice there's no overlap here between these two areas that we're counting. So therefore, there is nothing to take out for double counting. And that's why there's a 0 here. Punch all this out on your calculator and out comes 0.127. This then is our probability that a randomly selected subject is less than 26 and more than 55. It's actually coincidental that it's the same number that we got previously. The math just happened to work out that way. Here's another question. What is the probability that a randomly selected subject is over 65 or someone who responded? Again, here's our math. So the probability of the first event, over 65, plus, which is symbolized with the or, the probability of the second event, which they actually responded to the survey, and they're going to subtract out all of the outcomes that are being counted in both of those events. When we do that, here's what we get. So here's the numbers, and here's how it all crunches out. So the probability of being greater than 65, we're going to take the part, which is symbolized right here, over 65, the 57 plus the 1 plus the 25. That's the part for the over 65 event, divided again by the whole. Now we're going to add the probability of those who responded. That's this entire row right here, those who responded. So now we've got 65 plus 156 plus 279, on and so forth. We're adding up the numbers in the whole row here. That's the part of the whole that actually responded. Divided by the whole, that gives us the probability of those who responded. Now we're going to subtract out those events that are double counted. Notice there's an overlap here with the 57. So we have to subtract this overlapping value out if we're going to avoid double counting. You can see that it's being double counted if you look at the actual calculation here with the math. See, the 57 appears here in this portion of the calculation, and it appears here in this portion of the calculation. So we're actually counting it twice. So in order to avoid double counting, what we do is we subtract out one of those 57s so that it's only counted once. When we do that, we punch all this out on our calculator and we get 803 over 972, which when we divide gives us 0.826. So 82.6% is the probability that someone is over 65 and responded to the survey. Or responded to the survey. This leads us into what are called Venn diagrams. Venn diagrams are simply visual representations of events within a sample space. They're usually represented with circles inside some type of rectangle. And so if we have event A represented by the circle on the left and event B represented by the circle on the right, if they overlap, then that portion of overlap is said to be an intersection. So they're intersecting, and that portion in the middle that you see there in red is the intersection of event A and B. Inside this space, event A and event B occur together. So we have both events occurring inside that space. If I'm looking at just the green space, okay, then that's only event A occurs in this space. Event B does not occur here because it's outside that circle for event B. Likewise, here in the orange portion, I have no event A occurring. It's only event B. So when we look at this Venn diagram and we consider how it is that we're calculating with the addition rule, this is why we have to take out those events that we double count there, subtract them out at the end. Because we're here at this intersection space, we've got A, we've got B, but then we have to subtract out one of these portions here so that this intersection area is not double counted. And we get only the area that's bounded by both the circles together. There are occasions where events A and B will not overlap. So where there is no overlap, there's no intersection, and events A and B are said to be disjoint. Disjoint events are also called mutually exclusive events, meaning if you have A, you're not going to have B. If you have B, you're not going to have A. They don't exist together. They cannot occur at the same time. So when your events are disjoint, the complements of your events are also disjoint. So they cannot occur at the same time as their complement. So everything that's not A is outside the circle for A, and therefore there's no intersection, therefore they cannot occur at the same time. Likewise for B, the complement of B, B bar, is everything outside the circle for B. Therefore, B and B bar cannot occur at the same time. This is just a rule of how we define the complement, and so events and their complements are by definition disjoint. Let's look at an example involving disjoint events. Remember, disjoint events do not occur at the same time. So, supposing we have this pair of events, let's determine whether or not it is disjoint for a single trial. So first we have randomly selecting a data CD from an assembly line that is free of defects. And then the second event is randomly selecting a data CD from an assembly line that has a faulty memory sector. Are these events disjoint or do they intersect? I'll give you a moment to decide. Well, I hope you said that yes, these two events are disjoint. Remember, disjoint events do not occur at the same time. So, if you have a CD that's free of defects, you cannot have one that has a faulty memory sector. A faulty memory sector would be a defect. So, either it has a defect or it doesn't have a defect. So, these two events are disjoint events. Let's take a look at two more example events. First, we have a voluntary survey subject reporting a favorite color of blue, and then we have a voluntary survey subject reporting a favorite color of red. Are these events disjoint? Well, again, I hope you said yes, they are, because if your favorite color is blue, then it can't be red. If your favorite color is red, it can't be blue. Now, perhaps you have more than one color to be your favorite. That is a possibility, but from the way this is written, it seems to be implying that your favorite color is one color and one color only, a favorite color. So we're looking at it's either blue or it's red. There is no intersection. It can't be both. Therefore, yes, these events are disjoint. How about receiving a phone call from someone who hates all ice cream and receiving a phone call from someone who hates vanilla ice cream? Are these events disjoint? Well, I hope you said no, these events are not disjoint. If you have someone who hates all ice cream, that person is going to hate vanilla ice cream because they hate all ice cream. Of course, so because there's an intersection there, that means these events are not mutually exclusive. They're not disjoint. There is an intersection there. Now, I don't know why you'd be receiving a phone call from someone who hates ice cream. I mean, everyone likes ice cream. I scream, you scream, we all scream for ice cream. So why is it, I mean, if I had someone like this calling me, I'd be like, okay, dude, who are you? I mean, how do you have my number? Because we're clearly not friends if you hate ice cream. What about randomly polling voters and finding one who opposes abortion, and randomly polling voters and finding one who allows abortion under limited circumstances? Are these events disjoint? I hope you said no, these events are not disjoint. There is an intersection between these events. So you have one person who opposes abortion under all circumstances, and then you have one who allows abortion under limited circumstances. But allowing abortion under limited circumstances means there are circumstances in which you will oppose it, and so therefore there is an intersection here between these two events. One who opposes it all the time, and then another who opposes it some of the time. And that some of the time provides the intersection between the two events. Therefore, they can occur at the same time, and they are therefore disjoint. Let's review the rules for complementary events. So remember that when you take the probability of an event and add it to the probability of its complement, you get 1. This is everything that comes out. 1 is everything. It's 100%. That's all you can have. So the totality of everything that we have is bounded within our rectangle, and we have A. Everything that's not A is outside the circle for A. Therefore, we add both of them together and we get the entire total sample space. We can calculate the probability for the complement of A bar, by just taking everything and subtracting out the circle in the middle. That gives us everything that's left on the outside here, which is the complement of A, everything that's not A. Likewise, if we take away everything outside the circle and subtract it from 1, then that gives us the probability for the circle itself. That gives us this area here. So there's different ways that we can run with this complement event deal, but all you have to understand is that both of them added together give you everything, so then you can subtract each of them from 1 to get the other. This sets us up for the multiplication rule. Now again, your textbook authors claims there are 2 multiplication rules for calculating probabilities. There's the formal multiplication rule, which you see here, and again, this is what we're going to be using to calculate things out. I'll show you how to do that here in a moment. So the probability of P of A and B. So the probability of A and B occurring is the probability that event A occurs in a first trial and then event B occurs in a second trial. Properly read, this is the probability of A and B is the probability of A times the probability of B given A. So B occurs given that A occurs first. Then we have the intuitive multiplication rule, and it's basically running through the same thing. So you multiply the probability of event A by the probability of event B, but you make sure that you do it in a way that there's no double counting. When you're using the multiplication rule, you have to consider whether events are independent or dependent and adjust your calculations accordingly. Let's explore what that actually means. So when we're talking about the dependency of events, things are either dependent or independent. You have two independent events, A and B, if the occurrence of one does not affect the probability or the occurrence of the other. Several events are similarly independent if the occurrence of any does not affect the probabilities of the occurrence of the other. So each of these events, no matter how many you have, are going to be independent if the probability of that event, each one of them, is not influenced by any of the other events occurring. However, if that's not the case, and you do have some change in the probability based on other events taking place, then the events are said to be dependent. Here we have an example here on the slide of dependent events. If you have 5 marbles in a bag and 4 of them are blue and 1 of them is red, and you take 1 marble at random from the bag without replacement, meaning you don't put it back in. So let's say you take a marble out and it's blue. So then you've got 3 marbles in the bag and 1 marble in the bag. So now you've got 4 total. Well, taking out that 1 marble without replacing it created a dependent event, because the probability of taking that first marble out and having it red was 1 over 5. There's 1 red marble of 5 total. If you take a blue marble out and then ask what's the probability of getting the red marble out, now it's 1 out of 4 because you didn't put the marble back in the bag. So it changed from 1 over 5 to 1 over 4. That act of not putting the marble back in the bag changed the probability of selecting the red marble. If you continue to select a blue marble out of the bag, notice that the probability continues to change from 1 to 4, 1 to 3, 1 to 2, and eventually 1 out of 1. You have a 100% chance of getting the red marble if it's the only one left in the bag. This is what we mean when we say events are dependent. The actual probability is changed because these other events occurred. So 2 events are said to be dependent if the occurrence of one of them affects the probability of the other. But this doesn't necessarily mean that there's a cause and effect relationship going on here. Okay? So be sure to keep that in mind. Let's look at an example involving drug testing. Suppose we have 50 drug users that are tested for a particular drug, and we have the following results. So 44 tested positive and 6 tested negative. So now, if 2 of the 50 subjects are randomly selected without replacement, meaning we're not going to put them back in the pool to be chosen again, find the probability that the first person tested positive and the second person tested negative. Okay, so let's tackle this. The probability that the first person you select tests positive is going to be 44 out of 50. That's the part over the whole. But you're not replacing that person back into the pool to be selected again. You're selecting without replacement. So when you go to calculate the probability for the second person, there are 6 people left that have negative test results because the first one you selected tested positive. but there's only 49 people left in the pool to actually select from. So your total has actually changed. These events are then what we call dependent events because the probability of an event occurring has changed because another event has actually occurred. To get the probability of both of them occurring one after the other, we're going to multiply the first by the second, go straight through, calculate that out, and out comes 0.108 or 10.8%. Here's another example. Marbles in a bag. So let's suppose we have a bag of marbles that contains 145 marbles. 16 of the 145 are green, and the rest of them are white. So let's say that randomly selecting that one of the 145 marbles, we get a green marble that comes out. We're going to call this event A. If we randomly select with replacement another marble, which means we take a marble out of the bag and it's green, and then we put that green marble back in the bag. And then we're going to take a second marble out. That's going to be event B. So now we're going to determine whether the given pair of events A and B are independent or dependent. Here's your 4 answer options. I'll give you a moment to read through those and make your selection. Well, I hope you picked answer option A because this is the correct response. The two events are independent because the occurrence of one does not affect the probability or the occurrence of the other. By putting that green marble back in the bag, the probability of selecting a green marble has not changed. So therefore, the events are independent. Again, the key word here is with replacement. So when you see with replacement, you know the events are independent. If you see without replacement, then you know that the events are dependent. Very important to get that straight because how you calculate your probabilities out is going to change whether the event is independent or dependent. Let's look at finding the probability of A and B, which is the probability that A and B both occur. First, let's find our sample space. So we have 145 marbles in our bag. This is the total, this is the whole that we're going to use for calculating the individual probabilities. Next, are our events independent or dependent? Well, we're sampling with replacement, therefore the events are independent. So here's our equation. We're going to use the multiplication rule to calculate out our probability. So first we're going to calculate the probability that A exists, and then we're going to calculate the probability of B given that A occurred first. So we calculate each one of these in turn and multiply them together. We just identify the events as independent. They are samples selected with replacement. Remember, with replacement means independent events. So each of the probabilities is going to be pretty much the same because in each event we're selecting a green marble, a marble with the same color. So we start out the probability of A and B is going to be equal to first the probability of A. There's 16 green marbles in a bag of 145 marbles. So the part over the whole. This is our probability of A. Because we put the green marble back in the bag, okay, the probability of B given A is going to be the same thing. So this is the part for event A, 16. This is the whole, which is the 145. Now our probability for B given A is going to be the same because we put the green marble back in the bag. When we go to take the second marble out for the second trial, we're looking at 16 green marbles in the bag, and there's 145 marbles total in the bag. So because we put the marble back in the bag, the part remains the same and the whole remains the same. So we have 16 over 145 multiplied by itself. Punch that out on your calculator and you get 0.0122. This then is the probability of selecting a green marble in 2 trials with replacement. Supposing, however, that we didn't put that green marble back in the bag when we went to take our second trial. Now what is the probability? Well, we're going to use the same multiplication rule, but notice how we calculate the probabilities is going to change. First, we find our sample space. That didn't change. There's still 145 marbles in the bag. And next, we're going to ask whether the events are independent or dependent. So now our events are dependent because we're sampling without replacement. So the act of not putting that marble back in the bag changes the probability that's being calculated for the same type of event. Let's calculate each probability in turn as we did before and show you how this is done. So first we have the probability of A and B. It's going to be the probability of A. This is the 16 over 145. And we've seen this before. There's 16 green marbles in the bag over a total of 145 marbles. So we have the part over the whole. Now we're going to do the same thing for the second marble that we take out of the bag. But remember, we did not put that green marble that we took, the marble that we took back into the bag. So the green marble we selected does not go back in the bag. That means now there's only 15 green marbles in the bag and 144 marbles total. Because we did not put the green marble back in the bag, there's one less green marble to select. So our part went down by 1. But because we didn't put the green marble back in the bag, the whole also reduces by 1. There's one less marble in the bag total. So both of these numbers have decreased by 1. So now we're taking 16 over 145 and multiplying by 15 over 144. When we punch that out on our calculator, we get 0.0115. This is the probability of selecting 2 green marbles, one after the other, without replacement. Let's look at another example involving steel rod. So we have a foundry that's actually manufacturing steel rods. So you basically cast out a basic ingot shape, and then rods are typically made through a process called extrusion. So if you've ever played with Play-Doh as a kid, and you remember how you had that little press that you could put the Play-Doh in, and you had the different slides so you could change the shape of the Play-Doh as it comes out of the press? Well, that's exactly what extrusion is. So you're basically taking this metal, and you could do what's called hot extrusion, which is you heat the metal up so it becomes more soft, so to speak, as it goes through the extrusion die. Or you could do it cold, which is just do it at room temperature, slam that sucker through, and out comes the material in the specific shape of the die. So that's basically how steel rods are made, or rods of any metal for that matter. Typically they're not going to be cast, they're going to be extruded. So let's say a manufacturer is testing a newly delivered lot. So we're manufacturing product and we've got steel rod that we're using for manufacturing our product. And so we call up the foundry and say, hey, we need some steel rods. Give us an order of 1,500. So they give us a lot of 1,500 steel rods. They deliver it to our factory. And so now, before we take those into our manufacturing process, we need to do a quality check to make sure that this material is up to standards. It's not that we don't trust the people we do business with, but we just want to verify that everything is on the up and up. So we take this 1,500 lot of steel rods, and if we were to test every single one of them, we would find that there's 276 defective rods in the lot. These are rods that don't meet whatever quality standards need to be met. So typically what happens though is that when you're doing a quality check on an incoming lot of material, you're not going to check every single piece. That takes up too much time. It's too costly. It uses too much manpower. It's simply easier if you just do some statistical calculations with a much smaller sample of the population. So instead of testing all 1,500 steel rods, we're only going to test 5 of them. And we're going to select them randomly from the lot. So if we do that, what is the probability that the manufacturer will accept the entire lot? What's the probability that this lot will meet our quality assurance standards? Well, the probability that all 5 of these are going to be good just follows from the multiplication rule. So we've got the probability that the first one that we test checks out. Then we have the probability that the second one we test checks out, the probability that the third one we have test out, the probability that the fourth one we have test out, and the probability that the fifth one tests out. So we figure out what each of these probabilities are, multiply them together, and that's the probability that all 5 that we test are going to be good. The probability that the first one we test is going to be good is 1224 over 1,500. Where did the 1224 come from? Well, this is the part of the number of good rods in the lot. We know that if we tested all of them, and this is the information that we're given, that there's 276 defective rods in the lot. So that means the probability that something's going to check out, we have to subtract out that 276 to get the part that's actually good, that would pass the test. That's the part that would pass the test divided by the whole, which is the whole lot of 1,500. This then is the probability that the first rod we test is going to pass and meet our acceptance criteria. The probability that the second rod we test will meet our criteria is 1223 over 1499, because the first rod that we test does not go back into the lot to potentially be selected again for testing. Once we've taken the rod out for testing, we don't put it back in. Therefore, we are sampling without replacement, and we have dependent events. Each of these testing events are dependent testing events because the probability of one happening changes the probability of the others happening. So that one rod that didn't get put back in, there's one less good rod that that we have in the lot, one less rod total in the lot, so each of those numbers goes down by 1. And we're going to see the same thing happening because there's one less good rod in the lot, so we decrease each of these by 1. That's going to happen for each of the other remaining probabilities that we need to calculate. For each rod that we test, and each of those rods passes our standards, because all 5, we want them to be good. So therefore, we're going to subtract 1 from the part and the whole for each one of these calculations that we see going forward. Once we have each of these probabilities set up, now all we have to do is multiply everything out. And thank goodness we live in the age of the calculator and the personal computer, because that makes calculations like this very, very easy. So we punch that out and we get 0.364 or 36.4%. This is the probability that by taking 5 rods out, randomly selecting them for testing, all 5 of them are good. Only a 36% chance of accepting the lot? It's not going to be very likely that we take this lot. We're going to be, if we know what we're doing and we want to stay in business, we're going to go push this material back on the foundry and we're going to say, hey, what gives? 36.4% acceptance rate? That's not very high. We can't have that, because then that's going to reduce the quality of the product we manufacture, and then we're going to lose customers because we're not producing a quality product. So yeah, this is the point where you go back and you try to say, okay, what's going on with this material? And if the foundry wants to stay in business, and especially if they want to keep this account on their P&L sheet, they're going to be taking a look at their operation, and they're going to say, okay, what is it about our process that needs to change, that we need to improve, because this type of acceptance rate is clearly unacceptable. You can see that these calculations can get really cumbersome. Supposing that we took not just 5 rods from the lot. Let's say we wanted to select 60 rods. Well, then we'd have 60 fractions that we'd be multiplying together. And you could see that this could really outdo the operation performance of a simple hand calculator. So there are methodologies that we can employ to get around this potential problem. In general, the probability of any sequence of independent events is simply the product of their corresponding probabilities. We're just using the multiplication rule to multiply stuff together. So for each one of the probabilities that we select, so if we have 3 events that we want to put together, the probability of A and B and C occurring is the probability of A times the probability of B given A times the probability of C given B, and so on and so forth for as many numbers as we want to put out there and calculate together. So this gets really cumbersome if you have a whole bunch of numbers that you're going to multiply together. Okay? We can make the calculation more manageable if we treat the events as independent. We can do this if the samples are small and drawn from large populations. It's rare to select the same item twice when you're having such a small sample from a much larger population. The common rule of thumb is that if your sample is less than 5% of your population, then it's okay to go ahead and assume that the events are independent, even though they may be dependent. This rule of thumb applies even if selections are made without replacement. So technically, the events are going to be dependent, but if we multiply them out together, then assuming that they're independent, we can get an answer that's close enough to the real answer that we can take it and run with it. How does the probability of accepting our steel rod lot compare by assuming that the test events are independent? So supposing that we assume that the events are independent, how does that make the calculation simpler? Well, first, if you actually look at what we were doing, 5 rods out of a lot of 1,500. 5 divided by 1,500 is 1/3 of 1%. So we're not exceeding that 5% limit. So our sample's small enough to where we can assume the events are independent, even though they're in actuality dependent. That greatly simplifies our calculation, because here's how it comes out. We take the probability of one of them checking out multiplied by itself 5 times. So we're raising it to the 5th power. So we take the 1 fraction that we had at the start, the 1224 over the 1,500, raise it to the 5th power, and out comes 0.362. Note that this value compares well with the 0.364 probability that we got by noting that the events were dependent. So imagine if you had 50 numbers that you were multiplying together, or 60, or 75, or 100, or 200. If your sample size is less than 5% of the population size, go ahead and just assume the events are independent, because the number that you get out is going to be really close to the actual answer if you didn't assume independency. Now, above 5%, this assumption breaks down, and the number that you get from assuming independency is actually much further away from the real answer. But here, where the sample sizes are small, you can see that the numbers are really close together, and so it's okay to make that assumption and greatly ease the calculation process. Let's look at an example involving chocolate. Of course, we're going to involve chocolate. I mean, you got to know. I mean, this is going to be like one of the themes for the class is chocolate. So we have management at a local chocolate candy factory that was commissioned to do a survey. And so the survey came out surveying 2,864 consumers. And of those surveyed, 198 of them reported buying chocolate from this particular company within the past month. So 198 out of 2867 means you've got some pretty stiff competition. So let's say one of the survey participants is randomly selected. What then is the probability this consumer did not purchase chocolate from the local company within the last month? Well, first we're going to look at our math. So here we're going to know the whole is easy to get. That's the 2867. That's everybody that was actually in the survey. The probability that one person did not buy. So first we have to get the part of the people who did not buy. If only 198 people bought, that means the remainder from the 2867 did not buy. So we subtract out the people who did buy to get the people who didn't buy, divide by the whole, the part by the whole, and out comes our probability. So the probability that one person did not buy from this company in the last month is 93.1%. As I said, you've got some stiff competition. If 15 of the survey participants are randomly selected, so now we're not going to select just one person, we're going to select 15 of these without replacement. So without replacement means what? That's right. Well, I hope you said the right answer. Without replacement means that the events are without replacement. So you're not putting it back in. So therefore the events are dependent. So now what's the probability that 15 randomly selected participants, none of them purchased chocolate from the local company in the last month? So we could separate this out and do 15 fractions multiplied together, or we could just use our assumption of independency, because if we take 15 and divide by the 2867, we get a number that's less than 5%. So even though these are dependent events, okay, we're not going to multiply 15 fractions out together. What we're going to do is just assume that they're independent because we have a sample size that's less than 5%. So if we take the 15 that we want to select and divide it by the whole, that gives us 0.005, which is less than 0.05, which is 5%. Therefore, we can make this assumption of independency. To do that, we just take the probability of one person not buying it, and we raise it to the 15th power because there are 15 people we're randomly selecting from the survey. So when we calculate this out, boom, out comes our answer, 0.342, or 34.2%. This is a much easier calculation than taking those 15 fractions we'd have, where we select one from each of the numbers for the part and the whole for each fraction, and then try to multiply all those numbers out. It would be very difficult to do that with most hand calculators. However, you can, if you're interested, actually perform the dependent event calculation in a spreadsheet program like Excel, and it will compute it out for you well enough. But you're going to find out in the end that the number's not that far removed from 0.342. So why go through all that trouble? Just take the easy road. And I'm all about easy. So there you go. Tree diagrams. Tree diagrams are ways in which we can actually make our sample space and actually get the total number of outcomes out. It's one method for doing it. And sometimes this can actually be helpful if determining the number of possible outcomes in the sample space is not too large. So here we have a coin that we're tossing 3 times. So the first coin toss, we can get either a head or a tail. Then from each of those outcomes, when we toss it the second time, we can get a head or a tail. And then from each of those outcomes, we toss a third time, we can get a head or a tail. So then the outcome could be heads, 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 or heads, heads, tails. And so you see the tree diagram here is just showing you the different routes you can take to get the final outcomes in your sample space. Notice that there are 8 values in the sample space. We don't, however, have to go through all of this rigmarole with the tree diagram in order to get the size of our sample space. We can actually make a prediction based on what we know of how to get the outcomes. So we've got 3 tosses of a coin, and in each toss there's only 2 possible outcomes, head or tails. So in the first toss we can either get a head or a tail, so there's 1, 2 outcomes. For the second toss, we likewise have only 1 to 2 outcomes for each of the different outcomes from the first toss, and then we get the same thing from the third toss. So notice how this is growing. Well, we can tally this up and say, okay, so from the first toss, we have, this leads us to the 8 possible outcomes that we get. So the first toss that we have, notice we can get 2 possible outcomes here. And then the second, each outcome has 2 possible outcomes. And then the third toss, each outcome from the previous toss has 2 possible outcomes. So if we multiply those together, we get 8. 2 times 2 times 2 is 8. Likewise, we could say that 2 to the third power is also 8, because we have 2 possible outcomes that we're repeating 3 times. So 2 to the third power, 8. That gives us total sample space size without having to draw the tree diagram. However, for some purposes and for some people, drawing a tree diagram can be very useful at seeing how the outcomes actually play out. Let's summarize the fundamentals of what we learned so far in this lecture. So here we have the addition rule and the multiplication rule. So when you see the word or between 2 events that you're calculating a probability for, you know that you need to use the addition rule. When you see the word and between 2 events that you're calculating the probability for, then you know you need the multiplication rule. Remember, you have to do your counting in such a way that you avoid double counting. So with the addition rule, you have to subtract out those events that are double counted between your A and B events. With the multiplication rule, you have to make sure that you select the events in a way that you're not going to double count them. That brings us to the end of this lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.